Let us start today's class. Today this is the second time we are meeting. In the last class we had kind of summarized or rather introduced different kinds of circuit components, right. You remember resistor, capacitor, resistor follows Ohm's law, capacitor C dV by dt, inductor L di by dt is the voltage across the inductor. All of these you will notice that I am drawing the current from top to bottom and I am placing the voltage plus minus from top to bottom. Okay. Why am I doing that? Because double E students think of it like a water system, where water is being pumped into the overhead tank and then water is flowing from top to bottom. Okay. That is the direction of the current and therefore, potential also. All right. I is always C dV by dt, V is always L di by dt. The other way round, you could have written it as V equal to integral I by C dt, but we do not want to write it that way. Okay. Why do not we want to write it that way? Because usually whenever there is an indefinite integral, there is an arbitrary constant that comes into the picture and we do not like arbitrariness, we like definite stuff. So, we do not like doing the integral method. Okay. So, we are only going to stick to derivatives. I is C dV by dt and V is L di by dt, not I is equal to V by L integral V by L dt. Okay. So, that is not what we are going to do. However, that said, all these circuit components are mathematical. Okay. They are mathematical objects for now. The voltage, especially the voltage and current sources, they are mathematical objects. There is no such practical physical device. Okay. A physical device like this will have to produce infinite power, which is not possible. All right. We also discussed mutual inductance. I hope you remember, right. Mutual inductance is like two inductors, but they are coupled. Okay. So, the way I set it up was V 1 is ordinarily L 1 d I 1 dt, V 2 is ordinarily L 2 d I 2 by dt, but then because they are coupled, V 1 will also have something which belongs to I 2 and that is going to be m d I 2 by dt. Okay. And similarly, V 2 will also have a part which belongs to I 1 and therefore, it is going to be that part is going to be m d I 1 by dt. Fine. So, this is also a component. All these components are passive. Why are they passive? They do not generate power. Okay. Very good. Just by the way, if we have just pause. Okay. So, if I have a device which operates in this quadrant, do you think it generates power or absorbs power? Does this device? Do you see the line? Yeah. When V is positive, I is positive, it absorbs power. Okay. So, this is active or passive? Passive, good. And what about this device? It produces power, right. So, any device which is operating in the second quadrant will be active. And what about the third quadrant? If it is over here, passive. So, I do not. And what about here? Active. Fine, are we clear? So, the passive device operates in first and third quadrants only, active device operates in second and fourth also. So, what about a device which operates like this? Is it active or passive? It is an active device. So, the device is an active device, sometimes it is producing power, sometimes it is absorbing power. The device must be active. Similarly, this device is also active. Okay. The passive device is the one that passes through 0. It has to pass through 0, not anything else. When V is 0, I has to be 0. Fine. Otherwise, you can't go from the first to third quadrant. All right. Any other way to go from first to third quadrant? No. You have to pass through 0, the origin. Okay. Sorry, this is just an aside. I thought I must mention this. Then in the previous class, we also studied linearity, right. Linearity has two parts, superposition and homogeneity. Superposition means V 1 gives me I 1, V 2 gives me I 2, V 1 plus V 2 should give me I 1 plus I 2, and similarly 2 V will should give me 2 I, 3 V should give me 3 I, and so on. Alpha V should give me alpha I, that is homogeneity. Fine, extension of superposition. R, L, C, M, these are all linear components, very good. And then diode is non-linear. Time invariance is also something we studied in the previous class, and we basically said that if I do the experiment today or tomorrow, it should not matter, right, that my system is time invariant. But whenever I bring in some flip flops, some memory elements, some hysteresis, okay, magnets, fine, those are all elements that will create time varying circuits or time varying systems. All right. In addition to the RLCM, we also have current controlled, voltage and current sources, 4 varieties. Okay. And lastly, I had talked about KCL and KVL. KCL being the total current going out of some space, some closed space is equal to 0, and KVL being the total voltage, the sum of all the voltage drops around any loop is equal to 0. Okay, this is where we had stopped. Great. So, today we are going to start with something new, right, and the new stuff that we are going to start is called graph theory. Graph theory is a part of maths, it is a sub branch of mathematics, and those who are going to eventually learn machine learning, who are going to do heavy computer science, those who are going to do other finance, then they all want to learn graph theory before they do these extra things. Okay? Much later, you are going to decide to do these things, if at all, much later in third year, fourth year. Then you will realize that graph theory was something that you learnt in first year as part of circuit theory, others are not doing this graph theory, right. The EE students, they learn graph theory right now. Why? because we are going to use graph theory to learn how to analyze circuits. All right, and there are some very interesting things that come out of graph theory in terms of circuits. Okay. So, we are going to study graph theory right here, right now. It is a branch of mathematics. It has nothing to do with nothing whatsoever to do with graphs that you have drawn in school. You have drawn some graphs in school, those are not relevant. Okay. For us, a graph means some nodes and some branches. So, I can have a bunch of nodes all right, and some branches, some connections between these so, this is going to be called a graph. All right. It is a loose set of nodes and interconnections between the nodes, these are called branches. It is all loose. Okay. All the branches are like rubber bands, they can stretch, they can shift around, the nodes can shift, move around, no issue. Fine. This is going to be called a, what is it going to be called? A graph. And let us label these. So, my graph G is the set is this okay? You are all familiar with sets, union, intersection, you have done all of this before, okay, good. So, this set A, B, C, D, E, F, G, this is going to be called a graph over here. Any questions, any objections? Nothing, okay. Let us also label the different nodes. The nodes are also part of the graph 1, 2, 3, 4, 5, 6. Fine, this is a graph. You can also talk about, so this is a graph which has nodes six, sorry. Okay. So, the nodes are from 1 to 6, the branches in this case are from A, B, C, D, E, F, G, H. All right, this is called the graph. We can also assign some directions, some arrows. So, just for fun you can assign some arrows to each of these branches. All right. And with these arrows, this graph is now going to be called a directed graph or a digraph. Fine. What is the difference between a graph and the digraph? Arrows. Okay. These arrows are random right now, but eventually these will align with directions of currents, hopefully, right. You can think of these as directions of currents in future, okay, or they could be directions of potential drops from plus to minus, that also you could think of in future. Okay. For now they are just there, we have just placed them randomly, they are called. So, this is going to be called a digraph. All right. Now, a graph could be connected or it could be disjoint. For example, if I remove H, C, if I cut H, C and D, suppose I cut these with scissors, right, what is going to happen? The graph will split up into two subgraphs, okay, two subsets, they are, and they are not going to be connected with each other. So, that is called a disjoint or a disconnected graph, fine. And if H, C and D, if they remain in place, nothing, if we do nothing about them, if they remain in place, then this graph is called a connected graph. So, everything is connected, okay. All the nodes are inside the graph, nothing is loose, okay. The graph is not split up into two separate graphs, fine. So, I have connectedness and I have disconnectedness, connected. So, these are the words that we are going to use, and disjoint. Okay. Connected graph is when there is some connection between all the nodes, you can travel from any node to any other node. Okay. There is some way to go from from 1 to 4 or anything, right, anywhere to anywhere you can travel, that is called connected graph. Disjoint graph, India, Pakistan, that is disjoint. There is no road to go from Delhi to Lahore, right, disjoint graph, whereas Delhi to Chandigarh, connected graph. Understood? Very good. Next, we are going to talk about the next concept is called the tree. Okay, so this was my graph earlier, and we are now going to talk about a tree in the graph. The idea of the tree is that the tree is first of all going to be a subset of the graph. So, my what was my graph? What was G? G was this set A, B, C, D, E, F, G, H. Okay. The tree is some subset. How do you write T? Like this? Okay. So, T is some subset. Is that the symbol for subset? Yeah, okay. So, T is some subset of G, fine, some subset. Now, this subset has the following properties. 1, it is still going to be connected. So, all the nodes are connected to all the other nodes, no India Pakistan business, okay. They are all connected to each other, that is very important. The second one, which is super important, is there are no loops. When we say no loops, what do we mean? We mean there is one and only one road between, or one path, one way to go between any two nodes. So, you pick any two nodes, there is a way to go, but there is only one way to go, there are no two ways to go to that place, okay, because if there are two ways to go to that place, then I will have a loop, I can keep looping around, there are no loops, there is no way to there is no loop in the system, which means that there is only one way to travel between any two nodes in the tree. Fine, this is the definition of the tree. So, the definition of the tree is that it is a subset, naturally it is going to be a subset of the original graph, but the way we are going to build the subset is that it is going to the graph has to remain connected, number 1, and number 2, no loops can be formed. So, there has to be a unique path between any two nodes. So, for example, over here are there loops? Yes. So, obviously, we have to reduce, we can't have everything, all right. So, first of all let us cut this, a few of them out, let us cut f out, okay, at least one loop less. Then what else can we cut out? C, okay, let us cut out C also, we still have a loop, you can cut out H. All right, now you have got a tree, fine. So, the tree is, so this whatever remains right now, so this tree is A, B, D, E and G. Fine, there are no two ways to go from anywhere to anywhere, there is at least one way to go from anywhere to anywhere. You can travel from any point to any other point, there is a road, all right. However, there are no two roads, there is only one road. Done. You have understood what is a tree? Is the tree unique? No, it is not unique at all. I mean we could have cut out other things also, right. There was one over here, one over here, one over here. Is this what it was? Yeah, we could have deleted other things. For example, I could have deleted A, I could have cut off A and G and D. That also was fine, okay. It would look different, but that would also be a tree of the same graph. So, the same graph can have many different trees, right. The tree is not unique. However, a tree can be built. It is possible to create the tree of a graph. What that tree is up to you right now. Fine, there are many ways to construct it. All right, how many elements should be there in the tree? No, graph had so many elements. Here the graph had 8 elements, but the tree has only 5 elements. It should have all the nodes, but branches, how many branches should be there? N what is n? The total number of nodes is n. Your name is Arman? Adib. Adib says that if there are n nodes, then n minus 1 elements in the tree. And he is right. Right. Notice that this graph had 6 nodes, 1, 2, 3, 4, 5, 6, and the tree has 5 branches. Okay. But somebody else over here has to tell me why Adib is right. Yes, your name is? Huh, tell me. Okay.
When we apply our fundamental theorem of, I don't know if it's called a fundamental theorem, but the theorem is the number of branches plus 1 equals to the number of nodes plus the number of loops. So when we
Yeah, that is what we are going to prove now.
yeah,
You are going backwards.
I mean still we can just
Why do not you go forwards? Start from 2 nodes. Okay. So, to prove this, we are going to start from 2 nodes and then keep adding nodes to our graph. So, let us start from 2 nodes. How many branches can be there in the tree? 1. There can only be one branch in the tree, because the second branch is going to cause a loop. Okay, there are only 2 nodes. So, a second branch will cause a loop. Okay, good. Now, I throw in one more node into the mix. This also has to be connected. Okay. But to connect this, to get this to be connected, I can add only one more branch. If I add another branch to the graph, I will create a loop. Okay. So, now I have 3 nodes, 2 branches. Throw in one more node, all right, and then you run your induction method of induction. No, yeah. So, throw in one more node. How many extra branches can I have in the tree? Only one. So, every additional node is going to add one more branch in the tree only, right. I can't have any further branches, because anything further will create a loop. So, one extra node means one more branch in the tree, all right. So, you start with 2 nodes has only one branch in the tree, and then keep adding one more node, one more node, one more branch in the tree. Okay. So, therefore, n nodes will mean that the tree has n minus 1 branches. Is this okay? So, this is what we are going to do. Fine. Okay, great. And now, yeah,
I did saw one proof using matrices that was too confusing that like how you do that.
no, you do not need any matrix. This is full, right? This is full proof. Yeah,
Yeah, but that is the calculation.
no, this is our proof.
So that one that I saw.
Okay, okay. Let us not worry about the those guys. All right. So, our tree has 5 elements because we started with 6 nodes. All right. All the remaining branches are therefore going to create all the other branches, the ones that we have deleted, right, those branches will create loops. All right. How many such branches? So, if we started with B branches, n nodes, all right, n minus 1 branches in the tree, how many branches outside the tree? B minus n minus 1 outside the tree. So, these are called links, or some people call it chords. Okay. So, the tree is like a tree outside, the plant, the nodes are the leaves, right. You can go from one leaf to another in only one way, there are no loops in the tree. Imagine the plant, ped, from one leaf to another leaf you can travel, there is only one way to go, there are no two ways to go. Okay. If you want a shortcut, then that is a cord or a link, you directly connect two leaves to each other, that is called a link. Okay. So, those are called links or chords, fine. So, every time you have a link or a chord, it creates loops. And therefore, how many loops do we have? B minus n minus 1, is this correct? What is this? So, in our case we had no. So, first let us form the set, which is the set of links C H F. Okay, this is the set of links, fine, links. So, you have the graph is split up into two, one is the set which forms the tree and the other is the set which forms the links, right. There is no intersection of these two, but the union is the whole graph. Okay. Links union with tree forms the graph, and links union with tree intersection with tree is empty, fine. Okay, good. Now, each of these links, each of the links forms a loop, all right. And some of you are saying there are only 3 loops in this, there are not 3 loops, there are many more loops, there are many more loops. So, this is wrong. B minus n minus 1 loops, no, right. There are many loops. I can see so many I can see, right, 6, I do not know, you guys can count better, right, but certainly more than 3, all right. This is one gigantic loop with all the outside, even that is a loop, right, A, B, D, F, G, H, that is a loop, A, H, E, C, that is a loop, B, C, D is a loop, E, F, G is a loop, but then A, C, F, G, H is also a loop, right. So, you have bigger loops which are big, you have all kinds of loops, many loops are there, okay, not just 3. So, let us not talk about let us not say that you form only 3 loops. However, what we are going to say is that we have 3 fundamental loops. Okay. Let us call them fundamental loops and we will see what is fundamental about these loops very soon, okay, why we are calling these fundamental loops. Let us call them fundamental loops. So, my idea is that each of these, so I will make loop number 1 with C and the remaining elements should be part of the tree. L2 should be H and the remaining elements should be part of the tree. L3 should be F and the remaining elements should be part of the tree. Okay, that is my plan. So, if you look at your graph, I had sorry which all C H F. So, C H and F. Okay. So, if I choose C, right, my tree is like this. This is the tree. Okay. So, if I choose C, C is connecting 2 and 4. It is a shortcut between 2 and 4. But if you go along the tree, then you can go through B and D. Okay. Along the tree, you can take B and D to go from 2 to 4, and therefore, B, D and C form a loop. All right, we are going to call this a fundamental loop. Next, H. H is connecting 1 and 6, it is a shortcut between 1 and 6. But if you have to go along the tree, you are going to take A, B, D, E to go from 1 to 6. So, therefore, my loop is, my fundamental loop is fine. And lastly, F. F is forming a shortcut between 4 and 5, and therefore, along the tree if I have to go from 4 to 5, I need to take E and then G. Okay. So, these are my 3 fundamental loops. This is how I am defining the fundamental loops. Okay. But so far we have only said how we have defined it. What is fundamental about them? What is fundamental about them is that I can make other loops using these fundamental loops. So, if I for example take L 1 union L 2 minus L 1 intersection L 2, then I will get a new loop. Okay. So, what is this L 1 union L 2 minus L 1 intersection L 2? Just check CHAE, is that a loop? CHAE, it is a loop. Okay, it is a new loop which is composed of those two fundamental loops just by doing union minus intersection. Similarly, I can do L 1 union L 3 minus, oh, it will not work because the intersection is null. There is no intersection between L 1 and L 3. So, that is not going to work. L 2 union L 3 minus L 2 intersection L 3. What is that? H A B D F G. Just check H A B D F G. Yes, it is a nice huge loop, all right, and it has come just by a combination of previous loops, right, previous fundamental loops. You could even combine a fundamental loop with a non fundamental loop which you have just composed, right, and just by this union intersection, union minus intersection, this is basically the idea, right. You can create more and more loops by doing unions minus intersections. So, any two, so you can combine one of these with L 1. So, this, so now you can combine this loop can be combined with L 1 and you will get yet another one. Okay. What will you get? B D H A C F G. Okay, that is going to be something new, H A C F G. Yes, you have got a loop H A C F G. So, all kinds of these loops can be constructed, right, just with the help of the fundamental loops. That is what is fundamental about the fundamental loops. Fine. Now, each of these loops is going to create one KVL, Kirchhoff's voltage law. We talked about it, right. A loop, around a loop, all the sum of all the potential drops is equal to 0, correct. So, each of these loops. Now, which loops are important, which loops are not important? Okay. You are doing linear algebra also, right. You have the concept of linear dependence and linear independence of rows. Yes, you have done it, not done it, rank of a matrix, not yet done. Okay. So, it does not matter what basically what we are talking about is that some of these equations, right. If I combine two equations and get a third equation, then that third equation is not really important, the first two are important. All right. Okay. X 1 plus x 2 plus x 3 is equal to 0. Suppose this is my equation 1 and suppose equation 2 is x 2 plus x 3 minus x 4 is equal to 0. This is equation number 2, and if the third equation happens to be equal to x 1 plus 2 x 2 plus 2 x 3 minus x 4 is equal to 0. Is the third equation important? No. Why not? Because it is a linear combination of the first two equations. Okay. So, this equation is not important at all. We do not need it. I mean it is correct, but we do not need it. We do not require it. When we are solving all the different KVLs, right, you do not require that extra KVL. All that we are saying is that when we are dealing with these non-fundamental loops, the KVLs that we will get are linear combinations of the KVLs of the fundamental loops. So, if I do a KVL along CBD and I do a KVL, so CBD, so this particular one. So, if I do a KVL along CBD and I do a KVL along HABDE, these two KVLs, let us do them. Okay. Let us write them out just for your benefit. So, CBD, oh it has to be a digraph, otherwise we can't do KVLs. I do not remember the original arrows, but this is what it is right now. Okay. So, along C voltage, so VC is the drop from 4 to 2, right, and then VB is the drop from 2 to 3, and then VD is the drop from 3 to 4. Is this okay? This is a KVL. Okay. And then the next one is HABDE. So, VH plus VA plus VB plus VD minus VE. Okay, E goes backwards. Fine. This is the KVL, next KVL for the second fundamental loop. All right. Now, the non-fundamental loop, what was it? L 1 union L 2 minus L 1 intersection L 2 was CHAE. Okay. What was that? That was VC minus VA minus VH plus VE is equal to 0. All I am saying is that notice that equation 1 minus equation 2 will get you this new result. Okay. And why did this happen? Because this loop was not fundamental. as per our tree. Of course, if you change the tree, it could end up being fundamental, but not right now. Right now it is not a fundamental loop. Fine, understood? So, the fundamental loops give you equations, fundamental KVLs, which are linearly independent. The fundamental loops will give you KVLs which are linearly independent from each other. These are the important ones. Okay, remember when you were in class 12, I do not know what you were doing, but when you were solving circuits, you got lots and lots of KVLs, KCLs, then you were juggling the KVLs, juggling the KCLs, right. Then some guy would tell you no, you do not need that KCL, do this KCL, then the teacher would tell you no, I have a shorter method, do this fancy loop and you will get the answer, right. This is what you were doing in class 12. It does not work that way. Okay. We do not want to do that. We want to do everything in a systematic way. In a systematic way, we want to do only the KVLs that we need to do. All right. How do we figure out what do we need to do? This is how we figure out, right. We do not want to do anything extra. Only the KVLs that are linearly independent from each other, they are the ones that we have to work with. And we know, first of all, we have the guarantee. How many such KVLs? Number of links. So, B minus n minus 1, B branches, n nodes, B minus within brackets n minus 1 number of links, that many number of independent KVLs we will get. That is the number of KVLs we will write, right, but not do not write like just some KVLs, not just some B minus n minus 1 KVLs. Next you have to figure out what is the tree, next you have to figure out which are my fundamental loops, right, which are the links, for each link one fundamental loop. Okay. Those fundamental loops will give you fundamental linearly independent KVLs. Fine. So, to get the linearly independent KVLs, this is what you have to do. You are not happy? You are happy, or is this too much work just to find out all the linearly independent? We will have easier methods, do not worry. For now, this is the method. Okay. This is understood so far? Clear? All right, good. Next important concept we are going to move on to, this is called the cut set. By the way, these are all sets, right. The graph is a set, the tree is a set, the loop is also a set, the links are a set. Okay. This new one, this is also a set, cut set. Okay. Cut set is the way you draw a cut, right, with scissors. Imagine holding scissors and cutting, right. You have the graph and now you can cut the graph. How do you cut the graph to make it disjoint? What is the set of branches that you will cut to convert this graph into two disjoint graphs? Huh? Any one from the tree? Yeah, but links are also there. Yeah. So, right, so that forms a cut set. Okay. So, the cut set is how do I cut it to break up the graph into two disjoint subgraphs, fine, and the set of branches that you are cutting, that is called the cut set. Okay. For example, H, C and D could form a cut set, or for example, B, C, E, G could form a cut set, correct. So, there are many cut sets like this. So, you could cut any which way, you could draw your cut like this, you could draw your cut like this, whichever way you want to cut it. Okay. So, there are two ways to imagine this. One is using a Gaussian surface like I have drawn, or you could even hold some nodes in one hand, hold the other nodes in the other hand, and then stretch and then cut in between rubber bands, right. You could cut the rubber bands that are there in between, that is also fine. Any which way you want to visualize, that is fine. All right. Now, Adib has already said what I needed to hear. He wants to cut along the tree, right. He thinks that the tree has an important role in making sure that the whole graph is connected, and to make the graph disconnected, I need to cut elements from the tree. Okay. So, he is absolutely right. The way we are going to do it is think only of the tree. Okay. Right now, my tree is in that bold lines, or actually let us make a fresh. Yeah. Okay. So, what was my tree? A, A, B, A, B, D, E, G was my tree, right. Now, if I cut let us say G, then how does it disconnect the graph? Right now, it does not, because the links are there. Okay. But suppose links are not there, let us forget the links. What is the responsibility of G? G is the branch which connects 5 to all others, right. 5 is connected to the rest of the graph using G, fine. So, let us keep 5 aside and the rest of the graph aside. Which are the links now I need to cut? Which link should I cut to isolate 5? F. So, I can easily make a cut like this, right. So, that is going to be a cut set, fine. Any question? No? All right. So, the cut set will have one element of the tree and all other elements coming from the links. Just like the loops, how did we have the loops? The fundamental loops, one element from the links and all other elements from the tree. Okay. In this case, in case of the cut set, we are going to have one element from the tree, all other elements from the links, from the set of links. Okay. So, how many such cut sets are we going to write out? N minus 1, 5 in this case. Okay. This is my plan. So, G and F form C 5. This is a links in the set of all the links, all right. And then E, what does E do? In the tree, the E is connecting 1 2 3 4 1 2 3 4 with 5 6, all right. So, I keep 5 6. How do I isolate 5 6? I will isolate 5 6 with the help of E, cutting E and H and F. Fine. Okay. Then D, D is connecting 1 2 3 with 4 5 6. Okay. So, how do I isolate 1 2 3 from 4 5 6? Fine. Then I have B, B is connecting 1 2 with the rest of the graph. So, my cut is going to look like this, right. Yeah, yeah, that is not a fundamental cut set, you will soon see. You can construct that cut set with the help of these. Okay. Your name is Rahul, Raghav. Okay. So, Raghav has pointed out that there are more cut sets, right. These are not the only cut sets, great, we will see them. Okay. So, with B I have what? H, C and B, and with A is cutting out only one, right. Fine. So, these are all my cut sets. Now, these we are going to call them fundamental cut sets, right, arbitrarily right now. What is going to be fundamental about them? Just like the fundamental loops, these are going to be fundamental cut sets, because I can construct other new cut sets by combining fundamental cut sets. Let us see. For example, Raghav talked about a cut set with B and D only. B and D only or something else? Just B and D. Raghav wanted a cut set looking like this with just B and D, but notice I have C 2 and I have C 3. C 2 is the fundamental cut set for B and C 3 is the fundamental cut set for D. And if I do C 2 union with C 3 minus C 2 intersection with C 3, then I get the cut set that Raghav wanted. Fine. So, like this you can construct lots and lots of cut sets, right. Many cut sets can be constructed just by forming the unions and subtracting out the intersections, and those cut sets are not the fundamental ones. Fine. Why are we doing this? Why is the cut set important? The cut set is important because it gives us a KCL, a Kirchhoff's current law. right. I can sum all the currents coming out of the cut set and that is going to be equal to 0. Yes. So, that is why it is important, the cut set is important. Which KCLs are important? The ones for the fundamental cut sets. All the other KCLs are linearly going to depend on the cut sets formed from the fundamental cut sets. Is this okay? You are unhappy, terribly unhappy. No, okay. Okay. So, for example, C2, okay, let us write it out. So, what does this mean? I A plus I H is equal to 0. Is it okay? First one, the arrows are important suddenly. Okay, whenever we want to write the KVLs and the KCLs, we have to deal with a digraph, we can't deal with an ordinary graph anymore. Directionality is required. Okay. Then C2, cut set 2, IH plus IB minus IC is equal to 0. Fine. Cut set 3, fine. Cut set 4, and cut set 5. Is this okay? Yeah. Oh, I have jumbled it up, is it? Then cut set number 2, IB plus IH minus IC, IB plus IH minus IC. cut set number 3, I d minus I c plus I h, I d minus I c plus I h. Cut set number 4, I e plus f minus h, e plus f minus h. Cut set number 5, g minus f, g minus f. Okay. So, the claim is that this matrix is linearly independent and has rank 5. Oh, you guys are not yet fine. All other equations will be derived from these, right. For example, the one that Raghav wanted, right, I b minus I d is equal to 0, he wanted that, okay. I b minus I d is equal to 0, that is what he wanted. But I b minus I d equal to 0 you can get if you combine equation 2 with equation 3, right. You just have to subtract equation 3 from equation 2 and you will get I b minus I d equal to 0, fine. So, all other KCLs can be obtained by combining these different rows, right, linear combinations of the different rows in this matrix. In this matrix different rows linearly, if I combine them, I will get all other possible KCLs, fine. Any questions so far? All of this analysis depends on which tree you started with. If I change the tree, everything changes, nothing, all of this does not matter, right. I change the tree and create a new tree. Remember when we started we said a graph can have many different kinds of trees, right. You can draw all kinds of trees for the same graph, but that is okay, right, that you go ahead and draw. Whatever tree you start with, you have to be faithful with that tree, right, faithful to that tree, and then you construct all these KCLs, all the KVLs. And what are we saying over here? That these KCLs are guaranteed to be linearly independent, and those KVLs, the KVLs for the loops, we did not write out the matrix equation in matrix form. You can write it out in matrix form also, right. It will be something similar, right, but it will be V A, V B, V C, V D, all right, and then a set of ones and zeros. Ones, so the elements in this matrix are only plus 1, minus 1 and 0, that is it. There are no 2s and 3s, no other, nothing else is there, only plus 1 is there, minus 1 is there, 0 is there. Okay. When is it plus 1? When the direction is the same as the direction of the link. We started with one link, we started with one element of the tree, right. When the direction aligns with the direction of the element of the tree, then it is a plus 1. When the direction is opposite, it is a minus 1, and when it is not a member of the cut set, it is not related to that element of the tree, then it is a 0, fine, that is the logic. Okay. The logic is important over here. Yeah.
Then the first row, shouldn't it be 0, 1 instead of 1, 0? The matrix. It's I plus IH equals 0.
Yeah. Thank you. Yeah, I had the G and H interchanged at that time. So, that is why it came out to 1 0. All right, any questions so far? Yeah.
This question is somewhat out there. It's not part of right now. But does changing what tree we choose changes the row space of that matrix?
The what space?
Row space.
What does that mean? Number of rows.
No, like space spanned by any linear combination of any of those rows.
Space spanned by the linear combination of these rows is the same no matter what. Right? It is the same. The space, the total space spanned by linear combinations of these rows is the same. It is the set of all KCLs. Right? The set of all KCLs are covered, that is the row space. Okay. I can change the tree, all right, or I could also move to a tree-less. Without tree, can I do something else kind of a picture? So, one possibility is, let me just make a new page. So, one possibility is that we look at each and every node and draw a cut set around the node. Okay. And these also will give me KCLs, right. These also will give me KCLs. Okay. If I just simply draw a cut set around each and every node. Now, let us forget the tree for a bit. This can correspond, these cut sets are not related to the tree anymore. They could be, right. For example, one of these cut sets made its appearance earlier also, right. AH is still there, right. Some of these cut sets could be the same, but never mind, we just systematically say we will go to every node and draw a cut set around that node, a cut around that node, okay, and write a KCL. Is that okay? It is easy to write, right. So, these KCLs, these are going to be called the node. At each node you are doing a KCL, right. You go to a node and do a KCL over there. Are they going to be linearly independent or dependent? They can be independent, but they might not be independent also. No, wrong. They are always linearly dependent. They are guaranteed to not be independent. Okay. Why? No KVL, I am doing only KCL. They will give n equations, but I have only n minus 1. I had n minus 1 cut sets. I had one cut set for each element of the tree, and the tree had n minus 1 elements. So, n minus 1 cut sets, alright, and these n minus 1 cut sets are supposed to be linearly independent. Why are they always going to be linearly independent? Because the element of the tree is unique in each of them, each of these fundamental cut sets. The tree element is unique, it does not appear in others. I am taking one element of the tree followed by other links, that is how I have made the cut set, right. So, n minus 1, they are always going to be linearly independent, because the element of the tree is unique in each of them. There is no way to combine it with other equations and get the same thing. Okay. Whereas, over here I have n, it is one more than what is required. All right. These are going to be guaranteed linearly dependent. Fine, and we are going to work on this in the next class, because I think time is up for today. So, we will work on these linearly dependent equations in the next class. Okay, thank you.